In our first part of our population PowerPoint series, we're going to be talking about how natural populations grow. And in doing so, we'll take a look at generalists versus specialists, which we've already done, but we'll review again. RNK selected species, survivorship curves, carrying capacity, and how populations grow with available resources. So again, here are your learning objectives. Make sure you review these. But basically, specialists and generalists are exactly what they sound like. Specialists need very specific resources and areas to live in, like the koala and the panda. They're so cute, aren't they? And then generalists tend to have a much broader niche, or they use a lot of different resources. Their tolerance is very high. So they're actually more tolerant to change than specialists. Specialists are a lot less tolerant to change. And so moving into RNK selected species, depending on the organism, you're going to have a different life strategy. And so our strategists, for example, insects, algae, bacteria, a lot of rodents like rats, rodents are strategists. They mature very rapidly. They're very short-lived. They tend to be prey species. They produce lots and lots and lots of offspring because they die off pretty quickly because there's very low parental care. So basically, parents kind of have them and forget them. Generally, our strategists are not endangered because they tend to be generalist species. They end up with population fluctuations, which we'll talk about a little bit in that last topic, 3.5. And they're limited by density independent factors, which we'll go into a little bit more further on in the PowerPoint. So these organisms are small, and we'll talk about survivorship curves, but they tend to be on the type 3 survivorship curve. Again, we're going to talk about that later. And on the other side, you have case strategists. So they mature very slowly, right? Humans are case strategists. So if you look at this list and think about humans, it might make a little more sense. So K, koala, I don't know. Anyway, they mature slowly, they're fairly long-lived, they tend to be predator and prey species. They have very few offspring in their lifetime or even at one time in one litter. They have high parental care. Most case strategists are endangered species because they are so specialized. The population size actually stabilizes near carrying capacity. They don't go through boom and bust like the R strategists. Again, we're going to go over that again later on in the PowerPoint. They're more affected by density dependent factors, and they physically tend to be larger if you think about these large species like the panda or humans, right? We're big. Elephants, the blue whale, right? All these large species are case strategists. And they tend to sit in the type 1 and 2 survivorship curves. So let's move on a little bit more, right? It's kind of a fuzzy line, though, that you're not one or the other necessarily. A lot of organisms kind of bounce between. It's a spectrum of life strategies. So on the one end, right, you have oysters who are super R strategists, and you have chimpanzees and humans which are super K strategists, right? But there is something in between, so there's a little wiggle room there. And the way that they are affected by invasive species are different as well because of their life strategies. So because case-selected species are more likely to be specialists, they're more likely to be affected by an invasive species, where in our selected strategists are more generalists, and so they're less likely to be an invasive species, and in fact they tend to be more likely to actually be one, because invasive species are generalists because they're using resources that they didn't have in their native environment. For example, both fish are gorgeous. However, the lionfish on the right there is an invasive species in the Atlantic Ocean. They're actually a Pacific Ocean fish, and they're voracious. They will basically eat anything. Like, it's pretty nuts. Whereas on the other side, you have this wrasse that is native to Belize, and it's just been annihilated by this lionfish. The lionfish is basically like just eating all its eggs and, just out competing the wrasse in general. So that's what happens with invasives. But like I said, these are selected species, tend to be more invasive species and if they're not invasive, less likely to be affected by invasives because they can make use of other resources. Moving on to survivorship curves. Again, pause here and take a look at the essential knowledge and learning objectives. So survivorship curves are these curves that can show the distribution of species by age and the number of survivors at that age. And so when you look at reproductive strategies and how they live their lives, this will affect how they survive throughout their lifetime. So for example, in a type 1, for example, humans, right, or a K strategist is a type 1. Organisms in type 1 have, few offspring, but they live for a long time. So organisms that are being born are actually staying alive for the majority of their lifetime and then dying off towards the end of maximum lifespan. Type 2 is basically having an even amount of mortality through its entire life, like a squirrel, just facing a lot of environmental issues that kind of kill them off, like cars hitting squirrels or whatever, right? Like that's a moderate amount of a death rate all along its life cycle, whereas an R strategist is a type 3 survivorship curve where you have a lot of organisms being born, but they die off really, really, really fast, and then they kind of level out at the bottom, right? They're actually, not that many that live to the maximum amount of time. So, so the survivorship curves can kind of tell us life strategies and reproductive strategies of different organisms. So like I said, type 1 and type 2, K species tend to live up in that area, whereas my R selected species are more type 3 survivorship on the survivorship curve. And so here's a little breakdown of life strategies again, right? Type 1 on the curve has very late loss in life, so the reproduction early in life. Most deaths are occurring at the limit of the biological lifespan, like way at the maximum lifespan. Very low mortality at birth and a high probability of surviving into advanced age. So death rates are increasing during old age, and like I said, some examples are humans, sheep, elephants. Type 2 is constant loss. Like I said, it's a moderate amount of death along the entire lifespan. And predation is affecting all ages. So I said cars, right? But I guess a more natural die-off would be, a prey species predating on these, predator species predating on prey species. So type 2 are usually the prey species, like rodents and birds. And so you also have these early loss survivorship, which is type 3, and you have a lot of offspring, but most don't get that far in life. Very high death rate for younger individuals. And so like sea turtles, right? You have these cute little sea turtles, and then the birds pick them off or they die in the ocean. Really, you just put out as many offspring and hope that some survive. And so in looking at these survivorship curves, like I said before, right, these 1 and 2 survivorships are K strategists, and these three are our strategists. And finally, we're going to look at carrying capacity and population growth. So I'm going to, say again, take a look at these on your own time. I'm not going to pause and read them off to you, but we're actually going to cover 3.4, carrying capacity, and 3.5, population growth and resource availability together. To me, that just makes more sense to explain them together, so I'm going to do that. If we look at a population from when it first moves into this empty niche, which, would be almost like primary succession, I guess. But, when a population is first starting out, because it's got to start somewhere, organisms will increase in population exponentially due to the fact that resources are completely unlimited. There aren't enough individuals to actually force competition. And so we call this time period the biotic potential. And so biotic potential is the time where a population experiences maximum growth, and it happens under very favorable environmental conditions. So maybe there's lots of light, the temperature is just right, tons of nutrients, tons of food, whatever it may be when we're looking at resources. And so as the growth rate slows and stabilizes, resources it happens because resources are more and more limited as we hit carrying capacity, which is the maximum amount of organisms or individuals that an environment can hold. And so depending on what kind of species, you'll either see fluctuations around carrying capacity, or if the populations grow too fast, it experiences some sort of overshoot and a quick die-off, and we call that a boom and bust, which we'll talk about in just a little bit. Like I said, the carrying capacity is the number of individuals that can be supported in a given area. And depending on what's going on in the habitat, will determine where your carrying capacity sits. So if you have a nice, undisturbed habitat, your carrying capacity will probably be pretty high. But as the habitat is degraded, let's say maybe through habitat loss or whatever it may be, sedimentation, who knows, depends on where you are, right? But as that habitat is degraded, your carrying capacity is going to drop. So your carrying capacity is really dependent on, on how good your habitat is. But, there are these limiting factors that keep this carrying capacity in check. And so you have food availability, space, water, oxygen, nutrients, sunlight, whatever organisms need, right? Those resources are limited. And so we call them limiting factors because they're limiting the size of the population. And going back to our R and K strategists, right? In their life strategies, K species usually are sitting right at their carrying capacity. And while in R species are really going through this boom and bust. So like a rhino, right, these K species are living all the way up at the top and trying to just stay stable, whereas these R species are having so many offspring that you have this overshoot of the carrying capacity and this really sharp drop in population because they're exploiting all of the resources and there's not enough to support those organisms. And then they're going to start growing again when the resources become available again because of that bust. So R species are more boom and bust, and K species tend to be sitting at carrying capacity and stabilized. And depending on who you are, right, or what kind of organism you are, you may be affected by density dependent or density independent factors. Obviously, they're all affected by both of them, but depending on your life strategy, you will be affected by one more than the other. So, for example, you have density dependent factors. So basically, as population increases, it will affect larger numbers of populations. So examples are disease, competition, parasites, predators, food availability, right? All of these limiting factors are density dependent. It matters on how many organisms are in that space, or individuals are in that space as well. And so, for example, on the right-hand side, there are these little brown bats, and you can see they have little white noses. There's this white nose syndrome that's affecting bats, and the way that it's described is like a carton of raspberries, where like if one bat has this fungus on their nose, because they're all packed so tight together, right? They're at high densities. They all get it, so it spreads like a mold on raspberries. Whereas a density independent factor, doesn't matter what size the population is probably going to affect it. So things like volcanic eruptions, temperatures, storms, drought, but then also like chemical pesticides. So like bacteria are affected by density independent factors. So our selected species are more affected by density independent factors because they're not sitting at that carrying capacity, where density dependent factors more likely affect more case selected species.